Okay, hello everybody. We start our lecture. Let me recall that I finished former lecture with one definition. It was definition 1. Let me recall function from d to y. D in x is called continuous. It is continuous at arbitrary limit point x0 of d in d. Maybe I'll add, to avoid this strange writing, i.e. limit as x tends to x0, x in d, f of x equals to f at x0. So, and to distinguish what happens, there is a question. I have a question about two paths test. It says that if limits along these paths are different, then function has no limit. But at the first place, if for the same x and y we have the same path, I don't understand. If we have different paths for x, y, it is not a function. Так, тут вопрос по can you zoom please? You can see clearly the board. Могут посмотреть. One dimension for trying to put that in one dimension for 2x, there should not be the same y. 2x, not the same y. If for the same x and y we have the same path, it is not a function of I don't understand the question. Okay. Okay, so yeah, this is first definition of continuity on a set, and the second definition, definition 2, a function f from d to y, d is a subset of a metric space x, is called continuous on d if for arbitrary open set g in y there exists an open set g tilde in x such that pre-image of g equals to d intersected with g tilde. So pre-image, let me recall what is pre-image. That is the set of all x's such that f of x equals belongs to g. So pre-image everything what will be sent to the set G. Okay, these are two definitions. Maybe to fix somehow, instead of definition 1, definition 2, I'll call them definition with limits, and that is definition with preimages. Just to distinguish between them, to avoid numeration of different limits. Now theorem 1 of this section. I think no theorems were before. So definitions of continuity on sets in metric spaces. With limits and with preimages. Are equivalent. Proof. So in fact both mean the same thing. And okay, let's start with implication definition 2 to definition 1. So with help of preimages we deduce definition with the help of limits. So we know that preimage of an open set can be written in such a form: D intersected with G tilde. And we want to prove definition 1, that function is satisfies definition 1. So suppose what we have to do, we have to prove such a limit for arbitrary limit point of x naught. So suppose x naught in D is a limit point of D. Then what is the limit definition? This definition is equivalent, by definition of the limit, Cauchy definition. For arbitrary epsilon greater than 0, there exists delta greater than 0, such that for arbitrary x in, okay, I will write x in D which satisfies the inequality, the distance, okay, I'll indicate the space here, or x naught less than delta, we have an equality, distance in y between f of x naught less than epsilon. So recall, what is it? That is metric distance in x, here distance in y. That is what we have to prove. So we have to prove this limit. So we need to prove that. Now look, we take arbitrary epsilon greater than 0, then what is this? That is equivalent to say that f of x belongs to epsilon neighborhood of f of x naught. That is precisely what is epsilon neighborhood in a metric space. Means this ball, or the set of such points. So, but epsilon neighborhood is an open set. So, let us put it to be equal G. So, that is open set. Once again, I take arbitrary epsilon greater than 0, right? And consider such an epsilon neighborhood. That is an open set, so let it be open set G, right? Then we know definition 2 is satisfied, right? What it means, for arbitrary open set G, in particular with our set, right, we can do it. Pre-image can be represented in that form. So, hence, by definition 2, it follows there exists open set G tilde, open, in X, such that pre-image of our neighborhood, epsilon neighborhood, can be represented as D intersected with G tilde. But I can indicate a point which is certainly in this intersection, in this preimage. Which point? X naught belongs to this preimage for sure. Right? Because what is this preimage? It consists of all points which will be sent to this neighborhood. The point f of x naught is for sure in this neighborhood. And x naught will be sent by f to f of x naught. Right? So for sure x naught belongs to this. And then, so we know this preimage is this intersection, hence that is D intersect with G tilde, right? In particular, x naught belongs to G tilde. But G tilde is an open set, right? So there exists a neighborhood, let it be delta neighborhood, which is in G tilde. That is because of open. G tilde is open, right? G tilde is open, That is the reason for this implication. Now, look what it means. So, if we take arbitrary x in D, right, such that, it was about limit, but look, here it is written like that, but in fact, I can forget about this, right? It was for the limit. But if we are talking about continuity, then look, if it is equal to 0, what it means? X equals to x naught, right? And if x equals to x naught, for sure it's true. So I can forget about this inequality when we consider. But in fact, it doesn't matter. So for arbitrary x in D which satisfies this inequality, what can we say? Look, what can we say? What is written here? X belongs to D and satisfies this inequality. It means X belongs to intersection of this neighborhood with D, right? Because this neighborhood precisely that inequality, right? And also in D. But U delta is here, right? So this belongs to D tilde intersected with D, and that is precisely preimage. So look what happens. X belongs to this preimage. What means X belongs to the preimage? It means f of x belongs to the neighborhood, right? And it means we have proved everything. F of x is indeed here, right? And we are done. So the first part is proved. Now the second part, how to deduce from definition 1, definition 2. So now we suppose that definition 1 is satisfied, so at arbitrary limit point we have such a relation. So let's analyze firstly points of D. So let X be an isolated point of D. What it means, isolated point? It means there exists a neighborhood U. I denote radius by delta x because it depends on the point. There is a neighborhood such that the intersection of this neighborhood with our set D consists of one point x. So what is isolated? What is isolated point? So what is isolated point? It means you can find a neighborhood which, when you intersect it with our set D, contains only that point, nothing else, right? That is by the definition of isolated point. Now, so, okay, that is how we consider all isolated points of D. Now, let X be a limit point. And of course, yeah, here I should consider all points in D only. Okay, then by definition 1 we know then limit as x tends to x naught, x is in D, f of x equals to f of x naught. And then I'll not rewrite, this chain is satisfied, right? Everything is satisfied. What is written here with the help of and in particular, look what it means. It means that, let me write the corollary. So there exists delta, and let it be delta x. So you see, here there exists delta, right? For a point x naught. Now there exists delta which depends on x. We consider continuity at x, right? So there exists delta positive such that so let us analyze what is written here. F of intersection of this neighborhood with D is in the intersection of U epsilon f of x. Yeah. So I wrote what is written here. So the image of this neighborhood intersection with D is in this epsilon neighborhood. Okay. For arbitrary epsilon. Okay, I should insert it, right? For arbitrary epsilon. Now, what we do now? Now take an open set G in Y. So, and for arbitrary y in G, there exists epsilon, let's say y, positive, such that the neighborhood is in G. Now look, what we do. Now I am interested in preimage. Look at the preimage, right? So, then, what we do now? We consider all points y and g in G, right? All points. And look at preimages. So, what may happen? Some of those points have now, in fact, I can proceed like that. So look, for arbitrary y, there exists a point. No, sorry, there exists epsilon, right? There exists epsilon positive. For arbitrary y, there exists epsilon positive, right? If y is equal to f of x, then I can find delta, right? If y is not equal to f of x, I don't care about this y. Forget about it, right? So, then I take union for all x in D of those delta x neighborhoods, right? So look what I do now. What are those delta x? So I consider all points in G, right? If they are isolated, then this is the criterion how we determine delta x, right? If this is a limit point, then what we do? We look at epsilon y such that neighborhood u epsilon y of f of x. So y is f of x, right? Is in G. And with help of this epsilon, just that one, right? I can find delta x such that this is here. right? So that is how I determine delta x for every point x in D. These are open sets, right? Open set, because every neighborhood is an open ball, open set. And union of open sets, doesn't matter how many open sets we consider, is open. So that will be our G tilde. That is an open set. Okay? Okay. Now we need to check. So the claim is that this preimage is precisely D intersected with G tilde, right? That is what we need to prove. This preimage is precisely our intersection. Okay, how we do it? So look, take arbitrary point. So equality of two sets we can prove by proving two inclusions. So firstly, prove that one. So take arbitrary point x in f minus 1 of G, right? Then it's for sure is in D. Why? Because we consider the function from D to Y, right? So preimages is automatically a subset of D. That is for sure. Okay. Now we need to prove that it belongs to G tilde. That is again automatically, because look at G tilde, definition of G tilde. We took union of all x in D of those delta neighborhoods, right? So for sure, if we consider, so look, if point is here, then automatically is in D, right? And we took union of all neighborhoods, right? Such that yeah, but wait a minute, something wrong. Yeah, something wrong is here. I can indicate what is wrong here. If it is an isolated point, there exists a neighborhood, right? But D intersected with preimage of, yeah, here I should take intersection with preimage, otherwise makes no sense. Sorry. Yeah, intersection with preimage, only this intersection should be considered. Yeah, okay. Because otherwise it's too much. So in any case, you see, this inclusion is automatical. I mean, because if x is here, then x belongs to neighborhood with center at that point itself. So the point itself belongs to neighborhood with center at that point, right? And we consider all of them. Yeah. So this inclusion is valid without that addition, but of course converse not true otherwise. Now converse inclusion. Converse inclusion, second inclusion. I want to prove that D intersected with G tilde is in f minus 1 of G. Okay, then look, So I take arbitrary x here. So it means that, or maybe I'll write here y. You will understand why I want to write like that. So y is here, right? Then it means that what happens? There exists x in D intersected with f minus 1 of t such that y belongs to this neighborhood. By the definition of d tilde, right? If y belongs to this union, then it belongs to some of those neighborhoods, right? Now, what it means, y belongs to this neighborhood? There are two possibilities. Either x is an isolated point, and in this case, what it means, y coincides with x, right? So it's automatically is in pre-image, right? Because we took intersection with f minus 1, right? Yeah. Otherwise, x is a limit point. If x is a limit point, then how we choose delta x? U delta x intersected with delta d is in pre-image, so is in pre-image of G. That is how we choose it, right? So if x is a limit point, then it follows that y belongs to pre-image. And that is what we wanted to prove. Because how we choose this delta x? Look. So y is here, right? F of y then over there. So y belongs to pre-image of that. And that is a subset of G. So y is in pre-image of G. Okay, maybe I'll write like that. Hence, y belongs to pre-image of U epsilon of f of x, right? Yeah, and then y belongs to pre-image of G. First conclusion. Yeah, so if x is here, right, then x is in D, because our function was from D to y, right? So pre-image is automatically a subset of D. With G tilde? With G tilde. Why it is in G tilde? Because every point of f minus 1 intersected with D, right, belongs to the neighborhood with center at that point, right? It is center of this ball. Okay, then theorem is proved. Good. That's rather long. Oh. And that is very nice tool. Prove many other theorems. We'll see. This using of pre-images helps a lot. So next theorem is an illustration. Theorem 2. The image of a compact set under, not under, by a continuous function is compact. proof. So we have arbitrary k is x, k is compact, and f is continuous on k. So f of k is compact. That is what we need to prove, right? If f of k is compact. So, how we proceed? By definition, what means compact? We need to consider arbitrary covering by open sets. So we consider arbitrary collection of open sets, open in Y, such that their union of G alpha covers our f of k. So we take arbitrary covering of our f of k, right? Now, theorem 1, by theorem 1, says that f minus 1 of G alpha can be represented as preimage of an open set by a compact mapping, or by a continuous mapping, sorry. So f is continuous, right? G alpha are open, right? Hence preimage, we can apply theorem 1. So is k intersected with an open set G alpha tilde, right? And that is valid for arbitrary alpha in A. Now look at those G alpha tilde, right? Look at their union. So what can we say then? Union of alpha in A of G alpha tilde intersected with k, what is it then? That is, by the definition, union for all alpha in A of preimages of G alpha, right? So that is preimage of the union. It's easy to understand that this is valid always. So there was a question about preimage. What is preimage and image? And exactly, preimage exactly is written here, right? What is image? Okay, image is here. Let me recall what is it. It was given at the very beginning. So one of main things just about functions and methods, right? What is it? That is the sets of all y in capital Y, such that there exists x and k, which is sent to y, right? That is the H. Okay? And by the way, it's good to recall it, because now look at this. So preimage of this union, right? Union covers that one, so I can deduce from this that preimage covers preimage of the image. And what is preimage of the image? It's k itself, because nothing except for k we consider. We consider just the function over capital K.
So that is precisely capital K. Okay, so what it means? If this union intersected with capital K is K itself, then it follows that this union contains K. And all of them are open. So that is open covering. Open covering of a compact set. So K is compact. K is compact. Hence, there is a finite subcovering. So there exists finitely many alpha 1 so on alpha capital N, such that union of all G alpha I tilde still covers our capital K. So, oh, sorry, I wrote intersection here, sorry, union, open cover. Okay. So we have finitely many sets G alpha tilde, alpha I tilde, sorry, which cover together our set capital K. Now, look what it means. Let me recall now. So, then it follows that if I took union of those sets and intersection with K, then this is capital K, right? Because if it covers K, then intersection is precisely K. But then look what they are. Preimages, right? So these are preimages of G alpha I tilde. And we have finitely many. Right? So look. Union of those preimages is equal to K, right? Then if we apply our map F to this union, then we have that F of this union is precisely F of K. And then we obtain that union of G alpha. In fact, what we can here, what is F of union? F of union, of course, is equal to union of F of, but F of F minus 1 of G alpha I tilde, right? That is need not to be the set itself. Why? Because look, sum of points here may have no preimages, right? That is why they will be not recovered. But that is a subset of G alpha I tilde, right? For sure. So then this is a subset of union of G alpha I tilde, and we are done. Because look how we started. We took arbitrary open covering, and we have found finite subcovering of this F of K. So it means indeed F of K is compact. So we are done. And then corollaries. In fact, one corollary, which is called Weierstrass theorem in Rn. corollary. Weierstrass theorem in Rn. If f of x1, so xn, is continuous on a bounded closed set K in Rn, then it is bounded on K and attains its supremum and infimum on K. Proof. So we had criterion of compactness in Rn, which says we had K is closed, bounded and closed, is bounded and closed, hence K is compact. Then F is continuous on K, hence theorem 1 today, not theorem 2, sorry, theorem 2, this theorem, right, says f of K is compact in R. I didn't write. No. K to R, of course. Real valued function we consider here. Weierstrass theorem is usually given for real valued function. So f of K is compact, and what it means then, if f of K is compact, then it is, once again, we apply same criteria. F of K is bounded and closed. So bounded means the function is bound on K, right? What means bounded f of K? So we can put our f of K inside a interval, right? An interval, bounded interval. Okay, then what means closedness of f of K? So consider supremum of all values f of x. It is finite, of course, right? Because we know the function is bounded closed set it seems empty set is okay. Non-empty, of course. Yeah, otherwise makes no sense. Non-empty. Non-empty, yeah. Crazy exclusion, but we have to do it, because empty set is compact by definition, for sure. So consider supremum of f of x. What means supremum? It means that for arbitrary epsilon greater than 0, there exists, okay, let it be capital M. Let me denote it by capital M. It's supremum, let it be capital M. For arbitrary epsilon greater than 0, there exists x in our set K such that M minus epsilon less f of x less or equal than capital M. That is what means supremum. It follows from the definition of supremum. So we cannot find a smaller bound for values than M. Okay, then what happens? Look at this. So I can choose epsilon 1, then 1/2, 1/3, and so on. 1 over m, and so on. So we have a sequence of epsilons, right? Then for each of them we can find its own point x, and that is, I'll denote it by xm. So there exists a sequence xm in capital K such that the following inequality is satisfied: m minus 1 over m less f of xm less or equal capital M, right? Then what we have? What we have? Then we have a sequence of points of capital K. Once again, by criteria of compactness, we have 3 assertions in this criteria, so which are equivalent: bounded closed, compact, and third, for arbitrary sequence in capital K, there exists a subsequence with a limit in K. It was third. So there exists a subsequence M K, let's say, such that limit as K tends to infinity xmk equals to x naught, and this is in capital K. In capital K. That is by criteria of compactness. Now look, f is continuous at x naught. And you see we have a sequence. Hence, limit as k tends to infinity f of x mk equals to f at x naught, right? But look, so we have the following inequality: m minus 1 over mk less than f of x mk less or equal capital M. So if k tends to infinity, then both tend to m, right? Because mk is an increasing sequence of natural numbers. Hence that follows as well, right? So you see, this sequence has a limit capital M. From the other side has a limit f of x naught. Hence they're equal. And that is what we wanted to prove. The grammar is the text. And corollary is proved. Corollary is proved. And you see, this is an analog we had in first semester, Weierstrass theorem for continuous functions on interval, closed interval AB, right? So it means that for Rn, arbitrary bounded closed set is an analog of closed interval in R1, right? That is a consequence. And if you remember, there were other theorems about continuous functions on an interval, namely Cantor theorem about uniform continuity, and also Bolzano-Cauchy theorem about intermediate values, right? Intermediate value theorem. So, in fact, Cantor theorem also is valid in this form. Practically, the proof is the same, but I don't want to spend time because, yeah, practically we will not use it. But instead of that, I want to give you Bolzano-Weierstrass theorem, but this is valid not for compact sets, no. We need to use other properties of interval on the real line. Namely, we need next definition, a set, let's say E in Rn, is called connected if for arbitrary x1, let's say x2 in E, of course different, otherwise makes no sense, for arbitrary such points, there exists a curve path let's say gamma and recall that what is curve, it means we have a continuous map from an interval to Rn, a curve such that both x1, x2 belong to gamma, and gamma is in E, what is most important. So what means connected? You have a set like that, and let it be with holes inside, but still it is connected. Why? Because if you take 2 points, let's say here and there, right, then you can find a path that is gamma, which contains both. Of course, I didn't say that x1, x2 are the beginning and the end point. It doesn't matter, because if it contains extra pieces, we don't care about other pieces. Okay, that is connected. And then next theorem, theorem 3, Bolzano Cauchy theorem in Rn. If f from E to R is continuous on a connected set E in Rn, then for arbitrary A, B in the image, and let's say C between A and B, there exists no, there exists. C belongs to f of E as well, right? So it means that there exists a point x such that f of x equals to C. So once again, that is intermediate value theorem. Proof. So E is connected. Hence, there exists a path gamma in E such that it connects, gamma contains x1, x2, such that f of x1 is A, f of x2 is B. I forget to prove one more theorem, so I will refer to that theorem and I will prove it later. Okay, so then what is gamma? Gamma is a curve. What means curve? So there exists an interval AB such that gamma acts from AB to E, right? And we can suppose without, that doesn't matter, gamma of T1 is x1, gamma of T2 is x2. So that is our curve, right? And the value of f at that point is capital A, and on that point is capital B, right? So that is E, and f is here. So A, let's say, B, doesn't matter who is larger, A or B, doesn't matter. So f of x1, f of x2. Right? And then what happens? Look, consider f of gamma of t. That is well defined. Why? Because our function f is defined on E. On E, right? So f is continuous, gamma is continuous, and then I said, I forget to give you one more theorem. Composition of two continuous functions is continuous. I'll prove it after. So it is continuous, on AB as a composition of continuous functions. Okay, then look, so what we have then? F of gamma of T1 equals to capital A, F of gamma of T2 equals to capital B. Then by Bolzano-Cauchy theorem in R1, one-dimensional calculus, right? We have, there exists T between T1 and T2 such that f of gamma of T equals to capital C. So we have continuous function on interval, Hence, it takes all intermediate values, in particular capital C, which is between A and B, right? But gamma of T is in E, right? Because gamma lies in E. That's important. Hence, we are done. Gamma of T is in E, and that's okay. Theorem 4, but of course the order should be different. Theorem 4. Continuity of composition. Let me give it in slightly more general situation, not in metric spaces, but Rm and so on. So, suppose f from E to R is continuous on E, which is a subset of R, let's say M. Gi from which let it be choose, let it be D to E. I from 1 up to M, no, not to R, are continuous on D in Rn, and for arbitrary x in D, G1 of x, so on, Gm of x is in E. So we have m functions, all together they form a vector function with values in E. Then the composition H of x equals to f of g1 of x, so on, gm of x, is continuous on D. Proof. I'll use definition 1, with limits for continuity, and for continuity we use Heine definition. So use Heine definition. Definition for limits. So then what we know, for arbitrary sequence, now let's say x, okay, k from 1 to infinity, this sequence is in D, such that limit as k tends to infinity xk equals to x naught, right, in D, we have limit as k tends to infinity f of xk, oh sorry, not f, g I of xk equals to gi at x naught, I 1 up to m. That is, I wrote definition of continuity in terms of limits, right? But look, roughly speaking, this definition was given only for limit points, right? But what is for isolated points? Let's say if x naught is isolated, right, then this is also possible. How? The only way is to choose constant sequence, right? To repeat xk infinitely many times, not xk, sorry, x naught. Repeat x naught infinitely many times. And no other possibility to choose a sequence in D which tends to x naught, right? So it means we can also consider isolated points with the help of this definition without any problem, because it doesn't matter. So the only possibility for such a sequence is when all terms are equal to x naught, at least starting from a mode, right? Only such sequences are suitable. Okay, so we have this. Then that is because of continuity of G. Continuity of Gi is used here. Now continuity of F. For arbitrary sequence y, k, let's say, k from 1 to infinity in E, such that limit as k tends to infinity of yk equals to, let's say, y naught in E, we have limit as k tends to infinity f of yk's equals to f of y naught. That is continuity of F. Now, what is about H? Composition. Now look, consider H of xk, which is f of g1 of xk, so on, gm of xk. So what we know, xk tends to x naught, right? Then look, gi of xk tend to gi at x naught, right? So put y naught here, right? Let it be g1 of x naught, so on, gm at x naught. And also yk equals to g1 of xk, so on, gm of xk. We had a lemma which says that if components of a vector tend to component of a vector, right, then vectors themselves tend to vector which is formed with components, right, with those components. C is a unique point? No. Why unique? C is arbitrary between A and B. Yeah. Okay, so look. We know that YKs tend to Y naught, right? And then we refer to continuity of F. So F of YK tends to F Y naught, right? Hence, this sequence tends to F of Y naught, and that is precisely H of X naught, as K tends to infinity, right? And that is precisely continuity of H. Now, that is composition, continuity of composition. And you see that with the help of those Heine definition, we can also extend properties, I mean, continuity of sum, continuity of product, continuity of ratio. We can extend to the case of functions of several variables as well, without any problem. Also, look, this definition, limit x tends to x naught, x is in D, right? F of x. We used it in metric space, but it is also very suitable for functions of several variables. If we consider, look, remember, examples of functions of two variables, and we consider limits along a path and along a curve, right? We could take D as such a curve or path, right? And that was particular case. And similarly, we considered limits, right? But also we can say, we can talk about continuity along path, along curve, along lines, right? Also iterated, not iterate limits, no iterated continuity. Instead of that, I'll say about continuity in variable. So what means f of xy? F of xy is continuous in variable x at x naught, y naught. It means we should fix y to be equal y naught. So y equals to y naught and is fixed. We consider function of one variable only of x. And so we consider restriction, or in other words, continuity along variable x varies along horizontal line, right? Analogously in variable y. Okay, that's all for today.